Today, we are lucky to be joined by Bob Glenn, our regional manager, and Rick Dey, our business development manager. With that, I would like to welcome Bob.
Thank you, Sharon. Hello, everyone, and thank you for joining us for this presentation. My name is Bob Glenn, and I'm one of the regional managers here at Teledyne ISCO. Before I hand it over to my friend and colleague, Rick Dey, I wanted to share a few things about our company. Teledyne ISCO is located in Lincoln, Nebraska, and was originally founded in 1958. We are a true manufacturer, not just an assembly house. We specialize in the manufacture of rugged instruments used by professionals in the water, stormwater, and wastewater markets to protect water quality all over the planet, and we've done so for over 50 years, having invented the world's first automatic water sampler in 1971. Even after a half a century, we remain a world leader in the field of automated water sampling, and we remain as committed as ever to finding new and exciting ways to apply our products to safeguard the world's water. The use of our sampler products and wastewater-based epidemiology studies geared towards early detection of coronavirus and in testing for the presence of PFAS forever chemicals in water supplies are just a few examples of how our products continue to be applied to safeguard water in our rapidly changing world. We thank you for your business and stand firmly behind our pledge to continue to build great products and provide quality service and support to all our customers for many years to come. With that being said, I'll hand things off to Rick. Enjoy the presentation.
Well, thank you, Bob. Many of you may know me. My name is Rick Dey. I've been with Teledyne ISCO now for 36 years, and I'm part of the Water Platform Group. So I'm very excited today to be presenting once again for you. And we'll talk about some, I think, very interesting and important things to consider when you're doing your flow measurement, flow monitoring. And we're going to initially start with a fairly detailed technical level of how area velocity sensors work, and just kind of explain, give you a good overview of that. And then we're going to talk about the pros and cons of each of those. We'll also talk about some of the expected accuracy ranges. So there's a lot of things that go into accuracy, and I want to make sure that everyone has a good understanding of what applies to that. Then we're going to talk about the technologies and the different ones and what's best suited for some of your applications out there. So hopefully this will give you some ideas. And then we're going to talk about how some of the new technologies, and I'm talking intrinsic safe, can keep you safe and in the public safe on hazardous rated locations. And we'll also talk about some things that we can do to keep you out of the manhole and also keep you safe. So we'll be talking a lot about accuracy and safety. Okay, this is the ISCO Flow Lab. A lot of you have seen this. We can use or test from 4-inch to 24-inch pipe. We have 3 mag meters on this flow bench, so we have a very precise flow measurement to compare to. Well, what do we do with this? We primarily use it for design of product, so it helps us with all of our area velocity technologies and any other technology we might be developing. So we feel that this is a very, very important part of what we have at Teledyne ISCO to help you and help everybody have better accurate data. And we determine the accuracy using these mag meters, and we can also define or set our product specifications based on a lot of this too. So we want to verify that we meet what we say we can. And we can also simulate a lot of various different hydraulic conditions that will affect the accuracy and the performance of those sensors. Okay, so what do you do if you have an application like this and you don't have a flume or a weir? We get this quite often. I've been doing this for a long time, and people say, I need to measure flow in this pipe. Do you have a weir flume? No. Your only option at that time was to use Manning formula, which Manning could be 20 to 40% off, so very inaccurate. So the best way to accurately measure something without a primary device is to use area velocity technology. Area velocity technology, Q is your flow, is equal to the area, and the area or wetted area we use primarily level measurement, pressure sensor, but you can also use an ultrasonic sensor. So there's different manufacturers out there that's their standard. We can do those as well, but there's both options available to measure that level. V is the velocity component, and Typically people use Doppler. That's pretty much what's the standard out there. And there are two different styles. There's a contact or what we'd call wetted sensor. And then there's a non-contact or non-wetted sensor. And that's what, again, the different above pipe sensors that I'm going to be talking about in a minute. Okay, so let's look at area velocity. This is a pretty good illustration of what we do. So again, our Q is equal to our A times our velocity, area times velocity. We use the area using a pressure sensor. We know the pipe dimensions. We calculate that wetted area. Once we know that, we transmit a continuous wave Doppler signal into the flow. We know the frequency we transmit, we know the return frequency, and we can calculate the average velocity. So very simple, which is one of the pros on this. Very easy install for the most part. If you get into deep flow, big pipes, then it's not so easy. But these are primarily used in smaller pipes, 10-inch, 12-inch, 15, 8, things like that. So the installation, you put it on a mounting ring, squeeze the ring together, shove it in the pipe, and away you go. So the installation can be fairly easy. They are typically more less cost than any larger pipe type device. And because they are used with data loggers, which wake up, take a snapshot, go back to sleep, battery life is considerably longer. Some of the cons, safety. So again, we're talking safety. Confined space entry is typically required to do a installation of one of these. I'll show you some alternatives to that here in a minute, but that's primarily the way you would do it. And then the accuracy is going to vary a lot with site conditions. So they're normally put into applications where we're looking for inflow and infiltration. That's their main use. And those applications are normally not very good applications. They may not have good hydraulics. They may not have good pipe size, dimensions, and things like that in that invert of that manhole. So a safe alternative to a confined space entry is the picture on the right. So here we can do an actual installation and removal without going into that manhole. So what the guy can do here is pull the strap, it collapses the ring, put it down in that pipe, shove it in there, and let that strap go, tie it off to the manhole rung, and pull the pipes, the poles out, and you're installed. And then when you go to remove it, all you have to do is pull that strap, it collapses the ring, and you just lift it out of there. So that is a very good, easy way to keep you safe and also improve the installation time. The picture on the left is a normal, what I would call normal installation in a manhole environment. So you can see this one, somebody's going down in there and you're putting a scissor ring in and the whole bit. So two different ways of doing it. But if you get into large pipes, typically anything above 15 inches, you're going to go down in there. Okay, so kind of give you an overview. To calculate the flow or Q, we need to know the pipe or channel geometry. So we need to know what size pipe or rectangular channel, elliptical, whatever it is. Then we use the depth of flow to calculate that wetted area. So we can do a depth measurement and we do the average velocity of that flow. So that's in a kind of a quick snapshot of what these devices do. And again, that's all our Q equals our area times our velocity. So let's look at contact or wetted sensor. And this is what it's all about really right here. Without getting overly technical, on the bottom scale, that's frequency. To the right of 0 is positive or positive velocity. To the left is negative velocity. We do a couple things and everybody does something I think fairly similar. When we transmit that signal, the first thing we do is adjust our gain, which is our velocity signal strength. And then we do a velocity spectrum reading. And what that is all of these signals that are coming back, we trim off the front back end and we do a weighted average of what's left over. And that's called our velocity spectrum. Anything above 20% on a normal area velocity is considered good. Velocity spectrum ratio is a negative component. So if you look at this chart, you'll see there's a little pink blip on the left of 0. That means it picked up some negative velocity component in that reading. And what that typically will tell you is that you had some swirling or something where the sensor thought it was going in a reverse direction. Very important information when you're looking at the quality and the accuracy of the reading that you're going to provide. It also helps you understand the hydraulics. I've seen a lot of cases where without rain, everything looks great. velocity spectrum ratio is 100%, which is what it should be. And then when you have a rain event, that spectrum ratio can drop way down, and that's telling you you have something going on that's affecting the hydraulics. So very important information. You don't see this spectrum, but it digitizes it and tells you what it is in a numerical format. Okay, so let's go to non-contact sensors now. Why use non-contact? The picture on the left shows a lot of debris in that channel. So you have, tons of whatever that is in the bottom. So if you had a sensor, ours or anybody else's, in the bottom of that pipe, you're not going to get any readings. In this case, even if you had a non-contact, there's no real water flowing, so you wouldn't get any readings there. So this is just a bad application altogether. But at least being above that, you have a chance of getting a reading. Also, on the picture on the right, this is a safety factor. So the one on the left really relates to accuracy. The one on the right is safety. Nobody wants to do this if they don't have to. So you got blowers, you got all kinds of stuff. So that is also putting people in a dangerous position. Okay, let's talk about some of the different types of technology out there. And I'm going to talk about radar velocity sensors. And this is a surface velocity sensor. And what it does, it transmits a radar beam, measures the surface velocity to calculate the average velocity. So it transmits, reflects off of ripples in the water to calculate that velocity. Some of the pros on these typically have long range, so that's good. They are out of the debris, so that's also a plus, and that means lower maintenance, which is, again, your safety component on this. Some of the cons require some surface ripples, so normally you need a little higher velocity, and they can be affected by adverse surface condition. Wind blowing one way, water underneath going the other. Okay, another non-contact surface velocity sensor is using ultrasonic velocity. And the way these work, there are two crystals in the front, and those are shown in green. Those are reading the level, and then the two in the back are reading the velocity, so which are in the yellow color there. So one transmits, the other one picks up the signal. It's basically measuring how long it took for that signal to get back to the sensor. The pro of this is some of the pros would be it's out of the debris, just like the other one, lower maintenance, so that's the safety part of it. Some of the cons, though, requires surface activity, so it needs something, so they're going to require a little higher velocity than some of the other ones. Versus surface condition, or vulnerable to some kind of conditions on the surface. And these can be installed, a lot of times they're installed on a ring, even though they're non-contact, they're above that flow, but they're in the pipe, so you may have to do confined space entry. By the way, all of them are going to require typically some sort of initial confined space entry to install. And once that's done, then you shouldn't have to do it. Lastly, I'm going to talk about the non-contact laser subsurface velocity sensor. And so what this thing is doing is it is measuring the depth using an ultrasonic, reflects off the housing of the sensor. So water can come all the way up to the bottom before it won't read that level. And then it uses a laser velocity sensor to measure the speed of the water. So it's doing a subsurface velocity measurement. Okay, so when we talk about the laser subsurface velocity measurement, we have the ultrasonic. Once we have that reading, then we do a laser measurement. And what that's going to do is that's going to transmit, and can transmit, doesn't always have to, but it can go multiple points across that channel. So it can read, again, up to 15 different velocity points. And that's known as a multi-point, multi-depth velocity reading. All of these types of non-contact sensors have underwent a lot of testing, a lot of third-party testing. Some of them MCERT, that's a European classification, and that's typically class 2 is below better than 4% of reading. ITRC is a very reputable test facility out in Cal Poly, San Luis Obispo, and then Alden Labs in Holden, Massachusetts. So all of these non-contact devices have went through a lot of third-party testing to verify that we all meet what we say we're going to meet. When we design our sensor, and everybody else out there, typically we're looking at probably large pipe, because large pipes, deep flow, dangerous, nobody wants to be in it. So if you can keep them out of the that environment. And then we also see a lot of small pipe applications now, which typically we classify anything less than about 36 inches as small pipe. Okay, so we're going to talk about some applications. Some of you have already seen this, but I'm going to go through it again a little bit and just give you my feedback on what technology would best work. So we look at some of these difficult applications. One would be high velocity, low level. Steep slope pipes are very, very challenging. Low level raw wastewater is also very challenging because typically any sensor is going to require 1 inch to be able to even read that. And for that case, if you have very, very low levels, you may be better off using a non-contact device. So even though it's small pipe, we're seeing a lot more residential monitoring where they're looking for personal property INI or private property INI. And the only way you're going to get that is with a non-contact device when it's below 1 inch. Slow velocity, anything less than about 1/2 foot per second is very challenging with any wetted sensor. So when you get into, again, residential collection system, that's going to be a challenging thing. Slow clean water. So we have wastewater effluent, and that's important for accuracy because you need to be as accurate as possible when you're reporting your effluent to the enforcement people. Chlorine contact or UV disinfection channels, another very challenging one, but an important one because you have to be able to manage and control like your UV disinfection lights and things like that. But that's a very challenging application. And then drinking water plant influent is also another one that we're seeing more and more applications like that. Stormwater. So we look at stormwater where you have a wide fluctuation in flow conditions. You have a lot of irregular shaped channels that make it very challenging for accuracy. A lot of times stormwater could be in a ditch and you don't know what that area is. It's going to change and shift and, you know, all over the place. So it's very, very tough to do. So here's a picture just to kind of give you an idea. This is a application, very low level, and that water was screaming down that pipe. You try to put an area velocity sensor in there on a ring and water just flies everywhere. So if you tried to do it with a standard AV, you're going to be incredibly, very inaccurate. So the only possible chance to do this would be a non-contact sensor. Another slow velocity application. So this one, you can see that laser dot on the water, but the water's like glass. So that's really, really challenging to measure. We're seeing more and more of these types of applications, so more than I ever knew were out there. Velocity below 1/2 foot per second can be very, very difficult. Most area velocity sensors, the problem is they can't distinguish between the signal and the noise. So that's called signal to noise ratio. Here's some of the data that we did testing on. You'll notice that dash line in the middle was 1/2 foot per second, which is our spec in the case of the laser, but it can read down far below that in some cases. So they're all capable of doing some pretty amazing stuff. All right, so industrial monitoring, another one we're seeing more and more activity. Important here is accuracy. So there's a lot of money being moved around here in this deal, a lot of billing for treatment of the industrial discharge. What is really challenging is getting good accurate data. A lot of times people have flumes in there. The flume is designed with a throat that's narrow enough to catch the low flow, but when you have a high flow condition, it can't handle it. It'll either plug or surcharge and give you inaccurate data. So for that reason, the one on the left, that's a good picture of an industrial discharge. All they had to do was cut the top of that pipe out, and now they have a good hydraulic condition. They can handle low flows, high flows, pretty much the whole range. So that would be your best accuracy. And also safety is a major consideration when you're looking at this for non-contact, because you have a lot of hazardous chemicals involved, materials in there, who knows what's in there. And it's also typically rated locations. So it could be class 1, division 1. And I'll talk about class 1, div 1 here in just a little bit. Surcharge flow. Here's a good example of a bad application. This flume cannot handle the amount of flow. It's either debris in that flume or it's undersized for the capacity at this time. So they may have put it in years ago and it might have handled the amount of water they were discharging, but now it can't handle that. So when it surcharges like that, your accuracy is completely unknown. nobody's going to be able to give you a good guess on that. And the area velocity technology would be a better method. So if it were me, I would just tear that flume out, and I would go ahead and just put in a area velocity non-contact and be done with it. So also safety is a big part of this. We're looking at public health, overflows, we have backups, things like that that can cause you problems and affect the public health. Okay, so CSO, combined sewer overflow detection. So this is becoming more and more important as well. Accuracy is not as important because normally they want whoever is providing the data to give them how long it overflowed. Give me your best estimation of what that flow might have been. Okay. Also, area velocity is going to provide you much better accuracy than just a standard level only for the most part, but nothing's perfect in these types of applications. The data is going to be used to report the amount of the overflow, and this is also related to public safety, overflows, backups, and things like that. Raw water influent, we're looking drinking water. Drinking water, in this particular case, they had a pretty wide channel and they wanted to be able to measure as accurately as they could. They had two different lines that kind of fed off these so they could open a valve and pull water from each side. And for that reason, one sensor really wasn't going to do a great job for them. So they decided to go with two non-contact to do a better job of covering that entire channel. Safety is also a big one here because now you'll notice that little contraption they made across there with that I-beam, and then they have their sensors on rods sticking down, but they can remove it or install it without even entering the flow. So nobody wants to get into that water. That's very deep and very dangerous. Okay, another one, this is a river application. In this case, they went ahead and they installed 4 non-contact devices in there. They wanted to be as accurate as possible for reporting concerns. They did a dye dilution test on this, and they found they were within 1%, which is very amazing that they can get that. Now, one of the challenges again with a channel like this is that it's probably natural. So the bottom is going to shift and change. And so your cross-sectional area is always going to be a little bit suspect, but this is about as good as you can do. On the safety aspect of this, now you can install that sensor or remove it without going in there if you had to do any kind of repairs and those types of things. So another kind of idea for you to think about if you're in this type of application. Stormwater. We want to accurately measure stormwater as much as we can. Normally they're used to probably pace a sampler to sample that stormwater. So utmost accuracy isn't extremely important, but you want to be as accurate as you can to give the best representation of your sample of what's going on in that flow stream. Again, we're measuring the amount of water that's going to go into the receiving waters, rivers, lakes, and so on, streams. But they're highly variable due to hydraulics. So accuracy can be affected just because of the hydraulics. A lot of times there's nothing going through there or very little. And then when it rains and you have an overflow or you have something going on, it's just moving through there. And so you can damage sensors and things like that. Safety is a concern. You'd want to keep people out of there, obviously. And also non-contact sensors will keep your sensor out of the debris field as well. So we see a lot of these, you could have, God only knows what's coming down that line that could hit a cable and tear it out of the flow stream. But when we reduce our visits to the site, because we don't have to do that kind of maintenance, that also keeps our personnel safe. Okay, so high velocity river application. Some of the challenges here, we go from a low flow to raging rapids. So this particular site I was at, and normal flow is a trickle. And then when it does rain, that just picks up and just goes cruising through there. Any sensor on a cable is probably going to get ripped out. It'd be very difficult to get it securely fastened so it doesn't. And then the other problem is with wetted sensors, like I explained, a continuous wave or something like that, they're going to be accurate probably to the first couple feet. But when you get into, higher than that, then you're going to lose a lot of your accuracy because they just can't see far enough into the flow. So benefits of a non-contact sensor is it can read typically low flow and some cases very slow moving flow, can easily adapt to the high flow conditions. So reads the low flow and then that thing comes up. It doesn't care. It's going to give you a much more accurate method, and nothing is in the water. So again, we're accurate through really pretty much throughout the entire range, and nobody's in that flow and your sensors aren't getting ripped out. All right, wastewater treatment plant effluent accuracy. So that's important. We want to measure as accurate as possible the amount of water that's being discharged to the receiving water. Clean water and site conditions can have a major effect on the accuracy of that reading. So you want to have the best defined channels. Sometimes in effluent of wastewater plants, it just comes out of a pipe and then goes down a hill and away it goes. So that can be challenging as well if you don't have decent site conditions. From a safety aspect, you're going to reduce your site visits. The non-contact is going to improve obviously your safety of insulation and removal. So now you don't have to get into that flow. So installation is going to be much easier. Okay, drop pipes. So here's another one we see a lot of times in lift stations and different things like that, where the flow comes out above that and it drops out into that channel. There are methods of measuring that flow, and as far as accuracy goes, in this case, we're showing one of the lasers with a remote ultrasonic. So that ultrasonic is actually transmitting off of a reflector, hitting the water at the exact same spot where it's reading the velocity. So for accuracy, that is going to be your most accurate method. A standard wetted sensor, if you put that in a ring in the pipe, you're going to have a drawdown effect as it leaves that pipe that can affect the level as well as the accuracy of that wetted area. Non-contact, again, is going to keep you out of that channel, out of the flow. You're not dangling by a strap trying to put a ring in a pipe like that. Okay, submerged flow. This is another one we often get, is what happens when this thing goes underwater. These are normally mounted at the crown of the pipe, and then once that water level comes up and goes underwater, it will automatically switch to the other sensor, which is a continuous wave Doppler sensor that's mounted on the bottom of the sensor itself, but it's upside down. So now the nice thing is that it is reading the higher velocity, which is going to be towards the top of the flow, and it will give you much better accuracy than it would if it's mounted at the bottom. I'm not going to stand here and tell you that it's going to be perfect, but under these conditions, and if you look at that thing on the left, it's doing better than anything else could, I guess. Okay, so now that was the non-contact part. Now I'm going to talk about what else are we going to do to keep you safe. Well, what we're going to do is we're going to provide you with intrinsic safe flow meters. So now we have a hazardous rated, all of our sensors now, but there's a lot of them out there that are rated for class 1, division 1, or zone 0. Zone 0 is a European standard. But now we have a very high-tech way of measuring multiple locations, multiple applications, and we can do it while keeping you safe by providing intrinsic safe equipment. A lot of third-party testing went on to make sure that we still met our specifications, and we have a lot of international ratings as well. So intrinsic safe's a big one. They can be non-contact, they can be contact, whatever. So a lot of good things going on, and that's really we see as the way of the future. Okay, so I'm going to get close to wrapping up here, but I'm going to talk about a little bit about remote communications. I'm not going to beat that horse to death, but what's important about remote communications is now you're able to get data without going there. And the way we're able to do that is we now have intrinsic safe modems. So intrinsic safe modem tied in with an intrinsic safe meter and sensor now provide you the ability to safely collect data without going into that manhole, and keeps your people out of the confined space. And with non-contact, you're going to have reduced site visits, which will also help in the safety aspect as well. And then cloud-based software offers superior data security. So without going into the data security thing or cyber security, that's becoming a big issue now. So now we're able to give you intrinsic safe data, very accurate data, safe modems, so you don't have to worry about problems with explosions or whatever in that manhole, and it's going to keep your people out of that manhole. Also, event notification, there's a lot of alarming capabilities with cloud-based software, and what that will allow you to do is give you some sort of an alarm when something's going to happen, which will also enhance the public safety. Okay, so to wrap up, in summary, area velocity technology really offers a reasonable accuracy. I'm not going to say it's magmeter accuracy, but they do a really good job. For the most part, a standard area velocity sensor might be in the 5 to 10% range. A non-contact can be anywhere from 4 to probably 10. And they all can be very accurate, but they need to have reasonably decent hydraulic conditions in order for them to measure accurately. Non-contact is going to be really the way of the future as far as minimizing the maintenance and confined space entry. And we're seeing more and more, I am not letting my people down in that manhole. So we want to do everything we can to help minimize the amount of time they have to go in there. I will also point out that all of these sensors, or most of them, you can remove from the street level. So there's a street level tool that allows you have to go in the first time probably to mount the mounting bracket. But if you ever had to do maintenance or pull that sensor and clean the pipe, you can do that above ground with a street level tool to remove that. So that also enhances the safety. Intrinsic safe, can't say it enough. It's going to mitigate the risk of in rated conditions or locations. So now we are taking out the challenge of, or the problem of, possible explosions. I've been around a long time. I haven't seen one, but this is what manholes are rated as class 1 div 1. And so now we're able to, again, be able to read those and mitigate your risk. And finally, the remote communications provide provide data, hopefully it's accurate data, and limit your site visits. So have to look at all the different conditions you're dealing with, and every manufacturer is going to be able to help you, including us. And you call in and say, hey, I'm trying to measure flow here. What would you say, or what would you recommend? We have a lot of experience, and we're more than happy to help you determine what is best for your application to keep you safe and give you the best accuracy. And with that, I'm going to close it off to questions. And again, my name is Rick Dey, and Business Development Manager for the Water Platform Group. You can contact me at rick.dey@teledyne.com, and we'll be happy to answer any questions you might have if you think of them later. For now, though, we're going to go ahead and we'll open it up for questions. Sharon?
Well, thank you, Rick, for sharing your expertise. And it looks like we've received a few questions. If anyone else has questions, just enter them through the Q&A function, and Rick and Bob would be happy to answer. So with that, we will begin the questions.
Well, thanks, Sharon. So we'll look at the first one. What is the minimum flow the velocity wetted Doppler sensor will detect? It's really not detecting flow. It's detecting, obviously, the level and the velocity to calculate the flow. But most sensors can read down to about a half a foot per second. And depending, again, on the depth, I've seen them read, very low, 10, 15, 20 gallons a minute kind of flow. But it's more of how low that velocity sensor can read and what the depth is. So with our new sensor, the 350EX, I've seen data now where it's a couple inches deep and it's barely moving, and we're reading, a few gallons a minute. And it appears, that it is reading accurately, but that's always a kind of a tough deal. And that's where I look at something like that. And if you need to measure that real low flow, laser, in my opinion, or non-contact would be the best way to go on that. Let's see, we have another one. How do you calculate average velocity from a surface velocity reading? Very good question. I don't know exactly what they're doing with surface. They're taking that and multiplying by 0.9 to get average. With the laser, what we're doing is we're actually doing subsurface. So we are getting into the velocity profile as far as we can to calculate the peak, and then we take it times 0.9 to get the average. But as far as how the radar units do it from the surface, I really can't answer to that. Bob,
Hey,
did you have?
yeah, Rick, I'll take the next question. We have a question related to ISCO rental capability. And the question is, if our project is short term, does ISCO rent? Do you have plenty of rental equipment to handle a large I&I study, for instance? And the answer to that is yes, absolutely. We have a significant inventory, several hundred flow meters, area velocity devices, complete with modems, and we also rent a significant amount of sampling equipment. These are available for rental for as short as a 1 week period or for a year if you want to do that. So the rates for rental of these devices vary depending on the duration and the quantity, but generally speaking, we keep that equipment handy and in good repair, so that if a person has a pressing need and they need it shipped to them quickly, we can usually turn those shipments around within just a couple of days. So I would reach out to your local ISCO rep or contact us directly here at the factory in Lincoln, and we can provide some pricing for you if you have interest in ISCO rental.
Yeah, good stuff there. We definitely have a lot of rental activity going on, and we see that growing. And that's going to also involve the cellular communication side as well, the iCell. So, yeah, we're looking forward to that. How long do sensors typically last before needing replacement or repair? That is a tough question because it depends on, obviously, the application. We've had sensors that have been in, and I'm talking wetted ones, that have been in for 10 years and haven't needed any maintenance. We've had laser non-contact that have been in for at least 10 years and have not needed any kind of maintenance. So the key thing, I think, with what we do in our equipment is we store a lot of the diagnostic. I didn't go into a great detail, but the signal strength, spectrum ratio, and all that stuff, and then all the laser diagnostics help us determine, is there a problem with the sensor or the meter or not? So we're much better able to diagnose a problem remotely than ever before. So, but I would expect, we give 1 year warranty, and I would expect at least that. So anyway.
I'll take the next one, Rick. We have a question. Normally, these meters require equations to flows calculation. So where can I find more information about that? Well, in regards to the equation or the flow calculation taking place in these meters, I can speak specifically for the ISCO stuff in that all of our meters, or the data logging component of the meters, have these equations for primary devices and for varying types of channels, be it rectangular, trapezoidal, round pipe, elliptical, egg-shaped. All of those come preloaded in the instrument. So you just need to select what the flow conversion is or the shape of the pipe is, and then calibrate the instrument upon installation. And it will then, in generating a velocity and a depth value, calculate flow based upon that cross-sectional wetted area. Now, this may vary from one manufacturer to the next. Where you can find additional information about that is probably the best resource available out there is our own Teledyne ISCO Open Channel Flow Handbook. And if you go to our website, you can fill out a contact information page and order one of those handbooks directly from ISCO, or you can reach out to your local manufacturer's rep and they can get one of those to you. But it's a great resource. They give you lots of information about flow measurement, either via primary devices with a level sensor or by using area velocity.
Okay, thanks, Bob. I'll take the next one. By the way, we're getting some great questions, so I'm real happy to answer those. What kind of maintenance practices are needed, and how often should maintenance be completed? So that is a excellent question, one we get often. And what I would look at is on our equipment, at least, I'm speaking strictly on us, is we have a lot of diagnostics that, again, tell you the signal spectrum and all that stuff. That will tell you if the sensor is becoming covered with debris and if you have to do maintenance. You can alarm off of that stuff. So you go out, you install one, and your signal strength is 60%. And if it goes down to 30, I need an alarm because I'm getting covered with stuff. And so you can significantly reduce the amount of maintenance visits strictly by the alarm. And when you use a cloud-based software, you can set that up in your office to go. I had no idea this was happening here. I can set it up right there from the cloud-based software and alarm you, tell you to get out, change batteries, clean sensors, whatever. Non-contact also does kind of a very similar thing. And we store the spectrum reading, or what we call the Doppler power. And when you install that, it should be this, whatever it is. And then if that changes, then I need an alarm, then somebody needs to go out there. But with non-contact, you have a ultrasonic non-drifting sensor and a laser, in our case, that really don't drift. So there's not a lot of maintenance you need to do, and the diagnostics will certainly tell you if you need to do that.
Okay, the next question is, do you have any recommendations for using Mannings for a level-only flow sensor? That's a great question. Manning is an attractive option for people that have pretty finite budgets, and all they have is a simple level indicator instrument. The biggest challenge and my biggest recommendation for messing around with Manning equation to get a flow value is be very careful about your site selection. If you have a site that has the potential for any kind of a surcharge, meaning you've got standing water that is not moving, water backed up into a pipe, a site that's tidally influenced, or a site that frequently suffers from backups due to infiltration and inflow, poor hydraulics, et cetera, et cetera. You run into this in areas of older infrastructure more than you do in areas of newer infrastructure. Those are areas I would avoid using Manning, because Manning does not have the ability to give you a velocity value to consider when calculating flow. The other recommendation is, if you have a site that's got little or no chance of surcharging and has good free flow conditions through that site, you can get away with using a Manning equation, but it's very important that you put in accurate numbers for the channel slope and for the roughness based upon the composition of the pipe. Those numbers can affect the flow value or flow calculation of Manning pretty significantly. So that slope and roughness number, if you do get a site that's conducive to Manning, it's critical that you have accurate numbers in those two areas of the equation.
All right, thanks, Bob. Using the ISCO 2150 for open channel discharge measurements, however, having problems with negative readings when there are significant flow due to cross surface winds, any solution. I would need to see that data, because it depends on how deep it is. I suppose if it's an inch deep or something like that, maybe you could get those kind of things that could affect that. But if it's fairly deep, I would be surprised if you're getting negative velocities. That would be more, to me, a radar non-contact might suffer from that. But typically a wetted sensor doesn't really care what's going on the top. But again, the diagnostics that we have, the capabilities on that, we're able to tell you what that thing's reading. So feel free to reach out to us, and we'll want to look at the data and some of the diagnostic to help you determine that. So, but I would not expect that any wind would affect the velocity reading of a 2150. Okay, I'm going to take the next one. Please discuss challenges with low turbidity flows and laser flow. So turbidity and particles in the water and all that kind of stuff, TSS, any Doppler device needs some reflector. So it needs something, entrained air, whatever might be in that flow, but we need to be able to reflect our signal off of that. In the case of a standard area velocity sensor, like let's say a 2150 or ADS or Hawk or whoever, we're all transmitting and we're sending out a signal frequency, we're getting return back. And there's noise associated with that transmission. So the big thing is, how clean is your signal? How clean are your electronics to discern between the actual signal and the noise? The big thing with the laser is that it is so clean that it signal to noise ratio is incredible. So it can read very, very slow, very, very clean water. So when we use it at WEFTEC, which is the Water Environment Federation show, we use tap water, so it's right out of the faucet. We are pumping it, so you have entrained air in there, but we will also, the big thing is we can tell you immediately when you install one, looking at the diagnostic, are we getting anything back or not? So it's not going to be a guess. You're going to know when you install it, but sometimes until you install it, we won't know that. How are the non-contact sensors calibrated for the specific site conditions? Nothing magical there. We put in, like Bob was talking about earlier, the dimensions of the channel, whatever it is. We can do level to area. We could do any type of dimensions on that. So you put that in, and whether it's contact or non-contact, we put those values in. In the case of laser, what we would do is I would do maybe a depth multi-profile kind of thing to see what my hydraulics are looking like. If everything looks fairly normal, then I would go with a single point and just, again, depending on power, a single point or maybe a few points if you have AC power. But yeah, we really don't calibrate to specific site conditions other than the pipe dimension.
I'll take the next one, Rick. Question is, when would you rely on sensors versus creating a partial flume or weir to set up a more accurate hydraulic condition? That's a great question. I would, just speaking from experience over the years, I think you see people leaning towards using area velocity sensors rather than inserting a weir into a pipe, where you'd have the potential to back up the flow, especially in raw wastewater. Weirs within the collection system are not really a great idea because it creates an obstruction. It suppresses velocity, which then causes the organic material to want to bomb out on the upstream side. That can bolster hydrogen sulfide generation. It could create backup conditions potentially, which could cause problems. You don't want raw wastewater backing up into people's basements. Flumes are okay as long as they're properly sized. The challenge with the flume in a collection system, for instance, is that if it's undersized and you have high flows related to infiltration or inflow or something like that, when you really need to know what those flows are is the time that the flume can't handle it because it's overtaxed. And they also tend to constrict the flow on that high end as well. So if you have a large pipe, there's also significant cost associated with flumes, and not to mention the construction component of installing that, and that gets extremely pricey. So area velocity sensors are extremely effective in situations where you don't have a primary device like a flume or a weir, and they're also extremely cost effective. So there's a reason that area velocity technologies have really taken over that segment of the market in the last couple decades.
Okay, I'll go ahead and take the next one. First of all, I just want to say I'm impressed by all the Q&A we're getting here, and you have two of the guys that like to talk the most, Bob and Rick. So anyway, no, we appreciate this dialogue here. How to measure, it says no continued lagoon discharge flow. I'm guessing not continuous lagoon flow. And so the laser, in our case, the laser is designed to be able to handle really no flow. It doesn't care if it's dry pipe, doesn't hurt anything. It's going to reflect off the channel as far as the ultrasonic, and it's going to try to get a velocity reading. If there's no reading or no water, it's not going to get a reading, but it doesn't hurt anything. So but the one thing you do want to consider if you do an outside application like that is you would need a sun shield to go over it. And what that sun shield does is not protects really, but it keeps the temperature down on the level on the ultrasonic, which can drift with temperature. So that's the one thing to keep in mind on that. Bob, next one.
Yeah. Application with a 90-degree V-notch weir with very low flow, likely not even a half-inch deep. Is there anything to change that could work? Well, that's a pretty tough one. The low flows with the weir, extremely challenging. A lot of times you don't get that hydraulic jump through the structure that you're looking for. It's very, very challenging. So I'd say in this situation, the first thing I would probably do is contact the local rep, or send a video of the hydraulics at the site. Give us some information about the channel shape and size, and we might be able to make a recommendation. If you have a video of the actual water flowing at the site, that's helpful as well. The other thing I would say is, if you're talking about depths at a half-inch deep and minimal flow, and I think my colleague Rick would agree with this, and Rick, chime in if you like. But laser flow or a non-contact device, particularly laser flow, because it can read those lower velocities, would probably be the better way to go. And with that little amount of water, anything that's physically in the pipe tends to be a debris magnet, especially in a raw wastewater application. So I'd lean towards non-contact on this low-end flow measurement. It's kind of micro monitoring, if you will. But we've had some success, as Rick showed with a graph earlier in this presentation, reading really low velocities and low flow rates down below 10 gallons per minute with the laser flow.
Yeah. Yeah. When you get into that kind of condition, you're really, struggling to find something, but anything you can keep out of that flow is your best bet. And if it's slow flow, then the laser's really the only one that's going to read that low of velocity. So, okay, here's another one. Are there certain sensors that are more accurate with subcritical versus supercritical flow? Okay, I'm going to tell you right now, I am not a civil engineer, but what I would say from that is, if you can get a flume out of the game and just go with a laser, it doesn't care if it's subcritical, supercritical, blah, blah, blah. It is going to accurately measure that velocity up to 15 feet per second. So I'm not sure if I answered your questions or question on that one, but if you want, go ahead and email me and I will do what I can to contact the people that might know the answer to that. But I don't have a great answer for you, other than I would just go with laser, get any primary device out of there that might be involved in something like that.
I'll take the next one, related to discuss best way to advise a contractor to calibrate laser flow in the field during installation. And Rick may have some stuff to add to this as well. Really, all we're doing is we're calibrating the level once the instrument is installed properly. And that's the biggest caveat right there, is you really need to make sure that the mounting bracket, the hardware that the laser flow, I call it a cradle, sits in above the flow stream, is properly centered above the flow stream, is level. You verify that both the pitch and the roll of the sensor are at 0 and or within a degree of 0 degrees and 45 degrees, so that we know that the velocity is hitting the surface of the water at a 45-degree angle, and that our downward looking ultrasonic is striking it perpendicular to the surface of the water. That's the most important thing from a calibration standpoint, is just make sure that level is set accurately once you get the sensor properly secured and have confirmed that it is stable to the front and from side to side. Rick, you got anything to add on that?
Yeah, I would like to add a couple things. The laser has a built-in accelerometer like a cell phone. So it knows the X angle and the Y angle. And the X is the roll, should be 0 plus or minus 3 degrees. Y is the pitch of the sensor, 45 plus or minus 3. Anything off of any 1 degree off of 0 or 45 is about a 1% error. So the unique thing about laser is even if they don't get it perfectly installed, it will correct mathematically for that error in the angle. But the other thing that you're going to do is when the field crews install it, what they want to do is they want to measure the level. The laser is going to tell you where the water is. So it's going to get a distance measurement that says, oh, I'm 4 feet away from the water. And if you measure that entire range to the bottom of the laser and it's 6 feet, you know, you have 2 feet of water in there. So it is the most accurate way to calibrate the level in the field. You can always do the level measurement, but that is going to be the best, most accurate way to do it. All right, let's see. In a 750 area velocity module, how do I avoid spectrum errors during my programming? You need to probably talk to the tech support people, but if you're getting errors in velocity, then it's either covered in something or you have hydraulic conditions and things like that. But we would need to see the data. So you would need to get a hold of one of our technical support guys and let them look at that and work that through with you. So
Next question is about how many points IS laser flow can measure. It used to be less than the non-IS laser flow due to power limitations, but I wasn't sure if that was still the case. That is still the case. We do not do the lateral side-to-side profiling with the EX unit. This is about limiting the amount of energy that it's using. So we do multi-point profiling, but it's vertical, perpendicular to the surface of the water. So up to 3 points. Rick, did you want to add more to that?
Yeah, I would say that initially when the laser came out in 2013, it took about 45 seconds to get a reading on the laser. And now it's down to 2. And so for that reason, when we did initial testing, we did primarily a single point. We compared it to the ADFM, if you're familiar with that, which is acoustic Doppler flow meter, which was from MGD, which was a 2% device. And when we ran that, we found that a single point, provided the hydraulics are reasonable, was very accurate. But we do have limitations with the intrinsic safe rating. So like as Bob stated, we cannot do a horizontal reading like we can. So we would have to do 3 vertical. But at this point, it appears in all of our testing is we have no loss of accuracy if the hydraulics are normal. The other one will give you a better idea if you have really bad hydraulics.
Next question relates to warranty. 1 year question mark, or does it vary based on the flow meter being utilized? The standard warranty on all of our flow meter products is 1 year. And that's pretty much chiseled in stone. Rick, I'm not aware of any other models that carry beyond that 1 year of parts and labor.
No, we can, work extended warranty kind of thing, but yeah.
Yeah, additional warranty can be purchased for the instrument at the time that it's originally ordered and shipped, but our standard is 1 year. That is correct.
Yeah, and one of the questions right below that is, do we have a minimum charge for service work? I honestly can't answer that. We do have you have to submit a PO, and then I think I don't even know what we charge per hour, but we don't charge you like an $1,800 flat rate, because I know some of the other ones out there do that. We don't do that, but if you could contact us, I'd be happy to get you in touch with the right people and make sure we give you the right information.
Well, and it's also, I'll add this to that. There is a standard fee, and much the same as you, Rick, I don't know what exactly that is, but I do know that, let's say in the event you return an instrument, it comes back, and that instrument, you look at it and the cost to repair it or get it back up to snuff is more than, what you would consider. And you're looking at, might as well just buy a new unit. The labor that we put into evaluating that old piece of equipment, we will waive 100% of that cost if you choose to go ahead and purchase a replacement piece of equipment. So that's something that we do in the event that the customer decides, we're not going to go ahead and repair that, but we want to go ahead and move towards replacement.
All right. Another good question. does your equipment have provision for third-party calibration, such as dye dilution, flow rate testing, or a reference meter? Are we strictly limited to using something else for verification? One of the things that we did with the laser and even the new 350 AV sensor, area velocity sensor, is we can put a calibration coefficient. If you do a profile, you do a whatever third-party verification, dye dilution, and you feel that's more accurate, we can adjust the laser velocity or the 350 area velocity sensor to match what you want. I can tell you I'm not a big fan of that. Everything I've seen is the USGS rating is 0.85 to 0.95 feet per coefficient. So we take peak times that. What we found in all of our testing is 0.9 has been very, very accurate. I mean, well within 4%. But we've also done a ton of testing again with, like I spoke earlier, with the ADFM, that is a 2% device, and we sold that, and we actually put our own meter out of business because the laser was that accurate. But we certainly can do any adjustment with the meter if you think you need to do that. So, but we've tested pump station mag meters, we've tested flumes, all these different devices. So it is proven very accurate, provided your hydraulics are reasonable. Okay, for the non-contact sensors that are available, can they handle being submerged underwater? I can't speak for the other guys. I'm sure they're rated for that. What we do is we are rated at 6 feet for 72 hours. So when that laser goes underwater, the water's going to fill up, and it's like a diver bell. So the cone holds the water to a certain level, and it can go all the way up, way above that. We've had sensors that have been 20 feet underwater. That housing is extremely rugged and robust. When the water level comes back down, well, when it goes up, then we turn our AV sensor on, it takes over, starts reading the level. So now you're going to get an accurate level measurement of the surcharge, but it's also, if it's a, let's say 72-inch pipe, your flow calculation is going to use 72, period. It doesn't care if it goes 100 inches, but it's going to use that, and it's going to use a continuous wave Doppler velocity to measure the amount of flow going through that when it's underwater. Once it goes back down, it will seamlessly switch over to the laser level and velocity to calculate that flow. But they are very, very robust, and I'm sure the other ones are rated to be underwater as well.
Okay, next question is, what do you recommend for roughness value for RCP? I'm guessing that's reinforced concrete pipe. And off the top of my head, I don't know what that value would be. It's probably somewhere on the order of 0.01. But the nice thing about it is, if you do get a copy, a free copy of our Open Channel Flow Measurement Handbook, Chapter 6 related to the Manning formula has a table that includes estimated roughness values for all manner of different types of pipes and channels. So that information should be available at your fingertips if you can get your hands on that resource handbook.
Yeah, and that's one of the things I pointed out, I guess, earlier, is Manning formula was the way they did it way back, even before me, and it's very inaccurate. So you're going to be doing a lot of guessing on the slope, the roughness, and we really can't tell you. We can give you the handbook that says, here you go, here's your numbers. But it's a guessing game. You almost have to have velocity in order to get an accurate reading on that. Okay, here's another question that Bob skipped over. I'm not sure, he maybe didn't want to address it. No, he did. Is there risk of the sensor set in the pipe becoming dislodged and becoming blockage down the stream system? And yes, absolutely. And that's one of the challenges is you have a ring in there You have a spring ring, typically under 18 inches. So when you get down about 15 below, it is a stainless steel ring. We use a pretty wide ring. Some of the other manufacturers out there don't. They use a real thin one, but the wide one has a better chance, I think, of surviving that kind of condition. But yeah, if it gets blown out of there and goes downstream and plugs the outlet pipe, you got problems. And that's where, again, the non-contact would be prevent that from ever happening.
Yeah, Rick, I'll chime in on that too. And I didn't skip over it intentionally. It's just that there are so many questions today. I lost my place. So this is a good problem to have.
It is.
Is there risk with sensor set in the pipe becoming dislodged? Yeah, I'd say one thing to add to what Rick just said is from a quality control standpoint on your installation, it's absolutely critical with a wetted sensor that's mounted on a ring and then placed in a pipe to make sure that the cable of that sensor is properly zip tied down along that metal ring so that it's flush against the surface of the pipe all the way around the perimeter of the pipe. And if you're zip tying that on with plastic zip ties, make sure that you take the head of that zip tie, and when you trim off that excess, put that roll that over so that that head with that sharp little trimmed off edge is on the downstream side of the cable, so it minimizes the chance of rags and debris starting to catch on that. Because in raw wastewater, when you have these kinds of flows, all it takes is one rag to catch on that cord, and then it kind of, it's like tipping the first domino. Pretty soon you have a basketball size mass of rags that is being pushed on by the oncoming flow, and then that might potentially rip out the ring and sensor all in one fell swoop and cause a problem. So quality control on your installation in terms of securing that cable a lot of times is the thing that saves your bacon when it comes to avoiding dislodged sensors and blockages.
Okay. Let's see. I'm going to talk about this one here, which is, have you had any experience in placing wet sensors or non-contact in abandoned mine drainage systems? And what impacts do the minerals in the discharge impact the sensor? We actually do have some lasers in a mining application. I think it's in Brazil. And the water looks like concrete when it's going through there. And so they put a laser in there because anything in that flow is not going to work. It would be eaten alive in no time. So any wetted sensor is gone. So the laser was the only thing they could do. But if you do have a need for something like that, please contact me and I can certainly get you connected with what we're doing down there in Brazil on that.
Yeah, I'd agree with that 100%. I do believe off the top of my head that we have had a couple mine drainage applications here in the Rockies in the United States, and done some metering in those locations. And for the reasons you just mentioned, Rick, non-contact was the preferred technology.
Yeah. Yeah.
So I
just got a text. It was chilly. I was wrong. It was chilly.
Oh.
Anyway.
Next question, any recommendations, replacement of an existing Palmer bolus flume with laser flow? Well, we love that. We love whenever anybody wants to replace a flume with laser flow. Palmer bolus flumes generally don't have that big hydraulic jump that, say, a partial would or a trapezoidal would. So oftentimes you see these in lower velocity applications, and there's a potential for sediment buildup on the upstream side. By removing a Palmer bolus flume, you can bolster that velocity a little bit, create a little bit more scouring, and avoid those solids, which is great for non-contact. So yeah, absolutely. Laser flows would be a suitable replacement in a situation where you have a Palmer bolus that, let's say, frequently surcharges because of infiltration inflow. It's in your collection system, and it's just not sized properly.
And I'll add to that, Bob. With the Palmer bolus flume, you have that upper transition, as Bob discussed. So we're still a little unclear how the accuracy is affected. Like, let's say the laser, you put it upstream. What I tell people normally is whatever that you have D over 6 is your upper transition. So for easy math, let's say it's a 6-inch, you got a 1-inch, and I'll put a 1-inch silt level in that. If you have a laser upstream, you want to keep the laser and any non-contact as far away really as you can from those, and you're better off if you can remove it, remove that primary device if it's not working. But we can do both, and so we have applications now where we'll have a ultrasonic running on one of our signature flow meters that is reading the flow in the flume, and we'll have a laser upstream, and they compare both those. When we get into a submerged flow condition, then it would automatically switch to the laser and do its thing. But yeah, so that we don't know a lot about the flume. Just, I would say, keep it as far away as you can. Let's see. What are the typical reasons for seeing asterisks when an ultrasonic mounted on a horizontal bracket? There is a constant flow. However, there's a occasional asterisk on the level and signal strength. The sensor is mounted within a 48-inch underground or pipe underground. Any asterisk in any reading that you get is going to be, it's telling you I'm getting an error. I don't like what I'm getting. That ultrasonic on the laser is very, very robust. That thing has been working phenomenal. So what I would guess is we have maybe a programming issue, but what I would want to see is somebody download the diagnostic so we can see literally almost like an MRI of what that laser is seeing, both from a laser standpoint and an ultrasonic standpoint. So
yeah,
feel free to send it to me.
Mounted in a horizontal bracket too. So normally if that were a vertical mount, I would say if you're getting asterisks, you may have an issue related to your deadband, that the water level is too high and you have a deadband problem. But with the horizontal bracket, I'm assuming it's mounted, the ultrasonic beam is being transmitted initially anyway, parallel to the surface of the water before it gets reflected down to the surface. So either way, you could still have a deadband issue in that situation, but that would be where you're approaching a pretty full pipe.
Yeah.
So, and then our last question today is, how can I get the handbook? I've invoked the handbook on a couple of different cases here, and it's pretty simple. You just go to our website, which is at isco.com or Teledyne ISCO.com, and go to water, wastewater products, and then go to product overview. And then when you get to the product overview page, there'll be some radio buttons on the right-hand side. And the third one down, it's request a quote, upcoming past webinars, which you'll be able to get. This webinar will be archived on that site within the next couple of days if you want to go back and listen to it again. And then the third button is flow meter handbook. If you click on that and fill out a contact form, we can get one sent out to you.
Well, I think on that note, we've definitely set a record for the most attendees and the most number of questions asked. Certainly appreciate all the input, questions, and feedback. Feel free to get a hold of me or Bob at any time, or anyone at ISCO. And thank you so much for attending this. This has been really, really good.
Yeah, thanks for joining us, folks.